Okay. Remember, it's not just a power that concerns us, it's the signal to noise. So I want to look at the noise power, and we're going to use the same model that we used before with the communications link budget, where our model is that of white noise. So a Boltzmann's constant times a equivalent noise temperature. This gives a noise power spectral density, power per unit frequency, multiplied by the bandwidth, which has dimensions of frequency. So remember, this ideal case is I have white noise that has equal power in all frequencies going through a filter with a bandwidth B sub n, giving me something I can measure, a finite power. Okay, so the noise is going to depend on the bandwidth of the receiver, and going to see that has a different meaning when we look at the searching for a signal versus the example I gave here, where we can have a narrow beam and we're detecting the measuring the range or measuring the velocity of the target. And maybe I'm getting ahead of myself by bringing that up, but for now, just think the receiver has a finite bandwidth that gives me a finite noise power, but my model is the input to that receiver is this ideal white noise. Okay, so if I group all this together, I have a signal to noise ratio, which should be non-dimensional. Putting in all of this stuff. I think I'm going to move the loss closer to the noise terms. Squared, 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 and then K, loss, Boltzmann's constant, effective noise temperature, bandwidth. Okay? Now, the configuration I drew here might be a very general radar configuration. And what's general about it is I can put my transmitter pretty much anywhere in space and my receiver pretty much anywhere in space. The geometry is going to have a big influence on what this radar cross-section is, because I could imagine if I have anything that's not a perfect sphere, let's say I have something that is actually a flat plate of metal, and if I orient it, say, like I've drawn here, like this red, I'll get a pretty strong reflection. So that would indicate a large radar cross-section. But if I put it like, for example, like this, I'm only going to see a reflection, if I'm transmitting in this direction, off of a very small area. So see that my radar cross-section depends upon the geometry, okay? And this is a very general problem, but let's think of how most radars are implemented. Most radars, I'm going to be providing the transmitter and the receiver. And if I had this as drawn, I'm going to have to install the transmitter at one location, install a receiver at another location. Maybe one's on the ground and one's airborne, one's on the ground, whatever. Some radars are like that. Those types of radars, in general, are what are known as bistatic. Bi meaning two, static meaning stations. Two stations. And that's the most general sense. Transmitter, target. I just realized I'm using T for transmitter and target. So let's call this let's just use radar cross section. I'll just put a sigma there. Okay, that's the most general. And so as I imagine, I can get a large number of different configurations of this. Okay, most radars, I'm going to look at a limited set of configurations in which my transmitter and my receiver are at the same location. Maybe I have different antennas, but I'm going to simplify that and say that I have the same antenna. As long as I get this pulse repetition frequency correct, I can transmit, listen, using exactly the same antenna. And that's what most radars do. So in that case, then I have my radar cross-section reflecting back into the same geometry. So in that case, my radar equation simplifies quite a bit because my range to the target is equal to my range to the receiver is equal to my range. It's one range. Similarly, if I'm using the same antenna, my gain is the same for both. So in that case, my signal to noise ratio, it's a little bit simpler expression. Lambda squared, G squared, scattering cross section, transmit power, 4 pi cubed, range to the fourth, loss, K, effective temperature, noise bandwidth. Let me double check those. R to the fourth, LKTB, LKTB. Okay, and I believe this is the expression that is in the notes from MIT. Okay, so just keep in mind what the assumptions are. This is for a monostatic radar. Well, maybe I should say that monostatic, one station, in which I have the same antenna for transmitter and receiver. Okay, and I think if I skip ahead a little bit, the same equation is presented here, spread out, following the derivation that I gave. This is in terms of energy. So on Wednesday's class, we're going to go back and look at how we actually do that detection. But I get the idea that I've got to measure my reflected signal for some finite period of time, or a dwell time. So power times time gives energy. Remember from the communications link budget, we talked about an energy per bit. Same idea. I put a lot of blank pages in. I think I was going to use this much. Sorry about that. Okay, so this should be the same thing I had earlier. Okay, notice loss R to the fourth. So, you know, I have a big loss in the distance. Okay, so now what I do, I think we'll take a break, save this one, and then go into the next file, just so the files don't get too big, but I want to set up the problem I'm going to do next. In this case, this was the example where you can have a narrow beam, or you can define it by a gain, and I said this is maybe what I might call a tracking problem. I think that's what they call it here, tracking, where I know that the target exists, I know approximately where it is, but I want to measure the range. Now, the search problem, I don't know where the target is, so I could either have a very low gain antenna, an isotropic antenna, and illuminate a large area, or I can keep the same antenna and scan it somehow, either mechanically or electronically, and look for detecting of the target. And so I'm going to, in next section, I'm going to derive the version of this radar equation for the search problem, in which I need the ability to look over a larger area. Okay, so I'm going to record these, double check that everything worked out okay, and then go on to the next file.